All right, section 34 is on estimating with finite and infinite sums. So this is probably the most difficult section that you'll have for J-term. So let's go ahead and start. So we've learned sigma notation before. You've actually used it in previous math classes. So the first two should be pretty basic to you. So it says write the following in expanded form. So if we have sigma starting from I equals 0 going to 5 of 2i plus 1, what we're really saying is 2 times 0 plus 1. We find that result. And then we do 2 times 1 plus 1. And then we do 2 times 2 plus 1, and so on until we get to 5. So we're plugging in everything from 0 to 5. Now, obviously, you can do a lot of these steps in your head. I'm just kind of showing you in this expanded form. So if I have 2 times 0 plus 1, that's 1. 2 times 1 is 2, plus 1 is 3. 4 plus 1 is 5. 6 plus 1 is 7. So as you can see, you're actually getting the odd numbers. Does that make sense? So 2 times 4 is going to be 8, plus 1 is 9. And then 10 plus 1 is 11. So when you add those together, you get 36, I believe. So you're going to have 12, 12, and 12. All right, so this next one's a little bit harder because it has k's and n's. Usually our bottom variable is k, I, j. But in this case, we're just going to n. So it's doesn't have like a finite ending point. We don't know where it ends. Okay, so if I was writing this in expanded form, basically what I'm doing is I'm going to have 1 over n, and then I'm going to start with 1 squared plus 1. I don't know why I put that in brackets too. And then the next one is going to be 2 squared plus 1. But we still have that 1 over n out front. And then the next one is going to be 3 squared plus 1. And we're going to continue this pattern. So I'll do plus dot dot dot. We continue the pattern until we actually get to n. So we're going to have n squared plus 1. All right, so there's not much that you can do to simplify this. You could notice that they all have a 1 over n in front, right? So what we can do is we can pull out a common factor. We can pull that 1 over n to the front and then just have a big bracket. And then you can compute 1 squared plus 1, 2 squared plus 1, 3 squared plus 1, and see if there's possibly a pattern. So 1 squared plus 1 is going to be 2. 2 squared plus 1 is going to be 5. 3 squared plus 1 is going to be 9 plus 1, so 10. And there's not much of a pattern here. 4 squared plus 1, if you did that one, 16 plus 1, 17, and so on. So I would probably just do plus and then do n squared plus 1, like that, at the very end. So there's not much that you can do to simplify that. But we're going to talk about some more infinite sums like this. So when it goes to n, what do we do when it goes to n? Are there ways to simplify it? So if you remember, we talked about in Algebra 2 a guy named Carl Friedrich Gauss. And I told you a story about how when he was 10 years old, the teacher assigned the class of finding the sum of numbers 1 through 100. So it's debated. We don't know exactly what happened. Carl could have gotten in trouble. They said that he was kind of a bad kid, kind of rambunctious. And so they made him add up the numbers in the corner of 1 through 100. We don't know. So we don't know if the teacher had the whole class or just him. So Carl very quickly found the sum. And his teacher was kind of annoyed with that. Like, oh, why? You don't know that. That's not the number. It's not 5,050. And he was like, no, I did. So we talked about this before. Remember, if we're adding the numbers 1 through 100, it's best not to just, most 10-year-olds would say 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. And then they would add like that. Instead, he paired them like this. So we said, oh, well, 1 and 100 make 101. And 2 and 99 make 101. And 3 and 98 make 101, and so on. And he realized that there had to be 50 pairs of 101. So when he did 50 times 100 plus 1, he saw there were 5,000 plus 50. So the answer had to be 5,050. Okay. So Carl Friedrich Gauss was actually very instrumental in estimating with finite and infinite sums, and he came up with several summation formulas, which we use all of the time. So the first one is the one that we just talked about. It's right here. Okay, that's what I referred to as the Gauss formula in Algebra 2. It's taking the pairs, which was n over 2. So that's the number of pairs. Right, so if I had 100 numbers, that number was 50 then. And then it's multiplying by the first number plus the last number. So if it was 100, you have 1 plus 100 there. Okay, so that's all that this formula is. It's coming from that, what I call the Gauss formula. Okay, so you should already know this formula right here. It's saying if I'm summing up all of the digits, starting with I equals 1 to n, right, well, what does that mean? It means 1 plus 2 plus 3, all the way to n, right? That's what it's saying. So we already know that formula. And likewise, we kind of already know this formula over here, which is adding up all the digits of c. So let's say c was 5, and I start with I equals 1 and I go to 10. Well, that means I'm writing out 5 plus 5 plus 5. There's no I that I'm plugging in for, right? But I'm going to do that 10 times, right? 1, 2, 3, 4, all the way to 10. So if I have 5 added to itself 10 times, what do I get? I get 50. Okay, so those first two formulas are pretty straightforward. Okay, so you should definitely have those memorized. And the next two I will give you. So if you have these formulas and you need to know them, like on a quiz or anything, I'll give you those two formulas. All right, so it says use the summation formulas to find the sums. Verify with your graphing calculator. So it's going to seem a little bit strange, but it's using math that you know. Okay, so always think about, well, why am I doing this? Why can I pull this number out but not this number? Why can I do this? Okay, so for this first one, I have I equals 1 to 10. Now this would be very easy to do, exactly like you did in this first example here. You know, that's not super hard. Okay, so you could easily do that since you're only going to 10 using that method. But we want to know how to do it, you know, like if it said 1 to 1,000, like there has to be an easier way than writing out all the terms, right? So let's use these summation formulas. So for this one, I have I equals 1 to 10. And you always have to have I equals 1 in order to use these formulas. And there are ways to adjust it if you don't have that, but I'll give you always I equals 1. All right, so here we go, unless I want you to do it by hand, like those first ones. So what I'm going to do is I'm going to think about what this is saying first. So you don't have to write this stuff, just kind of pay attention to what I'm doing. So what I'm doing is I'm saying 1 squared minus 1 plus 2 squared minus 1 plus 3 squared minus 1 all the way to 10 squared minus 1. Okay? So if you notice, there's actually something that I can, a way that I can separate this sum. Okay, so what I'm going to do to separate is I'm going to start at I equals 1 and go to 10, but I'm going to say, well, I'm going to take all my I squareds together, and then I'm going to take all those minus 1s together. Well, how many minus 1s do I have? I have 10 of them. Okay, so what I'm really doing is I'm saying minus 1 from I equals 1 to 10. Okay? So I just have the minus 1, minus 1, minus 1, 10 times on the right side. Okay, so now what this I equals 1 to 10 of I squared is, it's using the formula right here. Our n is equal to 10. So I'm going to plug in. So I'm going to have 10, 10 plus 1, 2 times 10 plus 1, all over 6. And then this other one, so that came from here, this other one that I have right here is just, you know, it's the one where I just have a c. C is equal to 1. It's this right here. It's just minus 1 10 times, so I end up getting minus 10, right? So it's going to be minus 1, which was our c, times 10, which is our n. So as I simplify, I'm going to have 10 times 11 times 21 over 6 minus 10. And I continue to simplify. So like 21 and 6 are both divisible by 3. And then 10 and 2 are both divisible by 2. So 55 times 7. 55 times 7. Real quick. So 385 minus 10. So the answer to this would be 375. So again, it would not be super hard to do this, listing out all of the terms. You only have 10 terms. It wouldn't take you that long, okay? But if it said from I equals 1 to 100, this is when you're using the summation formulas, okay? So there's an advantage to that. Now this does say verify with a graphing calculator, so I'll do that in just a second. So the next one, okay, a little bit more complicated. There's a lot going on here. So you can kind of list out the first few terms if you need to see a pattern. But basically what I'm going to do here is I'm going to notice that I have a 3 in common on the top. Right, I can pull out a 3. And all of these are going to be over 100. So before I start this problem, I'm going to rewrite. And I'm going to pull that 3 over 100 to the front. And then I'm going to notice that I have I squared plus 1. And then it's over 1 now, right? Because the 100 I already pulled out. So it's like that. So if I was listing out several terms, I would have the 3 over 100, and then I'd have times 1 squared plus 1. And then I'd have 3 over 100 times 2 squared plus 1, and so on. So basically, I can pull out that 3 over 100 all the way on the outside of the sigma, okay? And you guys understand why I can do that, okay? So I can pull it out because it's a common factor to all of them. And now I'm simply computing this I squared plus 1. Well, the I squared plus 1 is very similar to what we did right here, right? So I'm going to break it apart. Because if I was listing out all of those, I'd have 1 squared plus 1, 2 squared plus 1, 3 squared plus 1. I'd have a bunch of plus 1s in common. Okay, so I'm going to break apart this sigma part right here. So I'm going to break it apart into 3 over 100. I'm going to do a big bracket. And I'm going to have the summation of I squared plus the summation of 1, which I think you guys should all know, right? If you have 1 plus 1 plus 1 plus 1, 100 times, you get 100 there. So that's coming again from here. So this one's going to be 100. Now the other one's coming from here, the I squared again. And it's a little bit complicated. It's 100, so we're going to have 100. 101, right? 100 plus 1. 2 times 100 plus 1, so 201 all over 6. And then the rest is that 3 over 100. So it's just a lot of simplifying, okay? And you can use your calculator to help you if you want. Now, in the time of Gauss, we didn't use a calculator, but I'll let you do that. So when I put this all in, I get the answer of 10,153.5. Okay, and that's our answer. You could find it as a fraction if you want to, or a decimal, doesn't matter. All right, so how do I do this with the graphing calculator? Okay, it's not super fun. I always forget every single year how to do this, and then I have to go back and think about it. Okay, so let's do this really quickly. So we're going to use a couple buttons that we haven't used before. Okay, we're going to use the sum and the sequence button. Okay, and the way that we find that is we're going to go to second list, and we're going to arrow over to math first. And we're going to go down to sum. Okay, so let's do the second example for this one. So if I go down to sum, and then I wanted to say sum sequence. Okay, so I'm going to do, again, second list, and I go back in there. But now I don't go to math, I go to operations, ops. And I go all the way down to number 5. Do you guys see where sequence is? Okay, and then the newer calculators will set it up like this, and I'll show you what the older calculators will do. But the expression is just whatever you had in parentheses right here. Okay, so we have the 3i squared plus 3 all over 100. Now we can't put an I. We're going to put an x. So I'm going to do 3x squared plus 3. Notice I put it in parentheses. So I have the entire numerator divided by 100. And then I'm going to end that parenthesis. and my variable is x, and I'm starting at 1, and I'm ending at 100, and I'm including every whole number between there. I'm not doing like 0.5 or anything crazy like that. So my step is by 1 each time. And when I hit enter, it's going to paste this into the field. Okay, so it's pasting it in up there. So when I hit enter again, it gives the answer. So we get exactly the same thing. Okay, so the hard part about this is a lot of people will mess up putting in the 3i squared plus 3 over 100. Or they'll just forget how to get that sum in sequence, and that's what I actually forget every single year. I have to think, oh, where do I find those? And I have to like play right around with my calculator a little bit. All right, now if you have the older calculator, you're not going to have that whole like paste thing. Okay, you're just going to have to type it all in. Okay, so what if you have one of the older calculators, what it's going to look like is you're still going to have to do that sum sequence. And then you're going to type in the 3x squared plus 3 divided by 100. And then you're going to have x, 1, 100, 1. Okay. So you're going to put in exactly what it had after you did the paste. But it's going to look, it's going to be a little bit different as you're doing it. Okay, and you should get the same thing. All right, so on your homework, make sure that you are showing the steps behind that. It is kind of nice checking sometimes that you can check. So make sure you show all your steps on your homework to check. All right, so you've heard stories about Archimedes before. I could tell you a bunch of really cool stories about him. He approximated pi using what we call an exhaustion method. So he found the perimeters of the circumscribed and inscribed polygons to approximate the circumference of the circle of a radius of 1 unit. So basically, if we have a circle with a radius of 1, okay, he found, you know, like a square inside and a square outside and found the perimeters, right? And then he went to a pentagon, and then he went to a hexagon, and so on. And he kept getting more and more sides on this polygon, so that basically if he had, I don't know, like 100 sides, it looks almost exactly like a circle, okay? So he did this by an exhaustion method, and he found a very, very close approximation for pi doing this. Okay, so we can actually find the area of anything, the area under any curve, using calculus. So if I wanted to find, whoa, I don't know why that one did that. If I want to find the area under this curve from like 0 to 4, okay, I do that by using calculus. Okay, so it says suppose you have the curve y equals x squared, and you want to find the area between the curve and the x-axis from 0 to 2. We're going to go ahead and sketch the region below. Okay, so we have a parabola. And we're finding the area from 0 to 2. Okay, so what we're doing is we're finding this area in here. Okay, so this is the region S, as we're calling it. So if you were trying to estimate the area, there's lots of different things that you could do. A lot of people say, well, I could use a triangle to approximate. So you could use a triangle here, but you would see that it'd be a little bit of an overestimate, right? There's a little bit more than what's actually under there. Okay, so then people would say, well, maybe I break it up into several triangles, or maybe, you know, a triangle and a couple trapezoids, right? That would be a good approximation. So there's lots of different things that you can do. So the first thing that we do in calculus is we use rectangles. All right, so what we're going to do is we're going to use rectangles, and maybe for the first one I only have 4 rectangles, like that. Okay, it's clearly an overestimate, right? Those 4 rectangles, if I add up the area of the rectangles, it's more than the area that's under the original curve, okay? But what if I did rectangles that were below as well, right? What if I did these rectangles as well, right? And then maybe found the average of them. Maybe that would be a little bit closer. Okay, so can you kind of see where we're going with this? So we're using rectangles. So it says, suppose we take our region S and we divide it into 4 strips. So that's what I just talked about, S1, S2, S3, and S4, with the vertical lines at those 4 places. Okay, so at x equals 1/2, 1, 3 over 2, and 2. Okay, we're going to use this to find what we call an overestimate. Okay, so I just had this drawing on the other page, but I'll do it again. So we're going from 0 to 2. 1 is directly between, so 1/2 and 3/2. And I'm going to do these little strips here. So S, this is strip 1, strip 2, strip 3, strip 4. All right. And I'm going to find the area of each rectangle using what I call right endpoints. So right endpoints start on the right side and go to the left. Okay, so see how I'm starting and I'm going this way to create a rectangle. So it has the endpoints filled in on the right. Okay, well, I would need to know the height of all of those rectangles. So what am I doing to find the height of the rectangle? Well, let's talk about this rectangle on the right. If I want to find the height of this rectangle, I'm plugging in 2 into our function. Well, our function was very easy. It was y equals x squared. So the height then is going to be 2 squared, which is 4. So I'm going to write these heights on the top. So I have 4. Well, the next one is going to be I plug in 3/2. So if I do 3/2 and I square it, I get 9/4. And the next one's going to be using the height of 1, right? See how that's the point on the right side? So 1 squared is going to give me 1. And 1/2 squared is going to give me 1/4. So those are my 4 different heights. So if I want to talk about the area of that rectangle, let's just talk about the one on the right side that I have filled in with blue. Well, that area would be base times height, right? Well, what's the base? The base is going to be from 3/2 to 2. And that distance is only going to be 1/2, right? From 1.5 to 2 is only 0.5. So if I want to talk about the area of the whole overestimate, well, maybe I should, instead of saying over area, I'll say overestimate. Our overestimate is going to be each of them has a width of 1/2, and then this first rectangle right here has a height of 1/4. And then I have a width of 1/2, and then I have a height of 1, and a width of 1/2, and a height of 9/4, and a width of 1/2, and a height of 4. So if I find this answer, I end up getting 3.75. Okay, and that's actually pretty darn close to our actual answer. So using, I told you that this is we're learning a long method now, and eventually we'll learn a shortcut. Our actual answer is actually 8/3, which is going to be like 2.6 repeating. So, I mean, it's not super close, but it's not too far off. Okay, and I wonder what happens if now we do an underestimate, if we'll get even closer as we take the average of those things. Okay, so we found the overestimate. I like to call this R4. R4 means right-hand endpoints using 4 rectangles. Okay, so let's do an underestimate. So in this case, an underestimate is going to use what we call left-hand endpoints. Okay, so we're going to divide up the region into those 4 numbers again. Actually 5 coming 0. So those 4 strips. But now when we do this, we're going to use what we call left-hand endpoints. So I'm going to start on the left and then go over. So the first rectangle is actually totally flat. It's not a rectangle at all. And then the next rectangle is like that. And then the next one's over here. And the next one's over here. Okay, so I'm starting with a point on the left side. So wherever it matches up on the curve, and I go to the right to create the rectangles. So all of these are under the curve. All right, and again, we need to find those heights. So the height of the very first one is 0. The height of the next one uses 1/2 as my x value. So 1/2 squared is going to be 1/4. Oh, geez, I don't know why my pen keeps doing that. And the next one's using a left endpoint of 1. So 1 squared is going to be 1. And then 3/2 squared is going to be 9/4. So my underestimate is still going to have a width of 1/2. The first height is 0. A width of 1/2 times 1/4. a width of 1/2 times the height of 1, and a width of 1/2 times the height of 9/4. So again, we find the answer. So our underestimate is 1.75. Okay, so we know that our true area has to be between our R4 and our L4. L4 means left hand with 4 rectangles. So left hand endpoints with 4 rectangles. So if we're somewhere between those two, doesn't it make sense if we're trying to find an even more precise answer to find the average of the two? So if I find the average, I do 3.75 plus 1.75 divided by 2. And this is going to be very close to my actual answer. So I end up getting 2.75. So I told you the actual value was 2.6 repeating. Okay, and I found that using some little shortcuts in calculus, okay, which you'll learn later. But we're pretty darn close, and we only used 4 rectangles. So how can we become even closer? Well, what if we use 10 rectangles, or 100, or 1,000? Okay, and if we wanted to find an exact answer, what we would do is we would use an infinite number of rectangles. That's what calculus is all about, using infinite sums, like limits, right? So that's what we're going to do next. So we're going to find an infinite number of rectangles. So it says you would think that if you have an infinite number of rectangles, its sum would be infinity, but it's actually not. Okay, so you can always kind of think back to the classic example of 1 plus 1/2 plus 1/4 plus 1/8. Okay, so let me show you on the number line what's happening here. So I'll go from 0 to 2. So if I have 1 plus another 1/2 plus another 1/4 plus another 1/8 plus another 1/16, and so on, it's basically going to fill that whole number line up to 2. Okay, so it's going to be like 1.9 repeating, which is actually 2. Okay, by using something similar to limits, right? So we end up getting 2 there. So you can have a finite sum with an infinite number of numbers. You just have to make sure those numbers are getting smaller and smaller and smaller, right? So it says, let's do a practice problem with an infinite sum before we talk about how this is related to area. So we're going to use kind of those formulas that we had before, but we're going to have kind of a complicated problem. Okay, so when you look at this, it's pretty darn complicated. Okay, so this is something where you might have to pause, think about it, rewind, right? It's a pretty complicated example, but it's going to lead to finding this exact area. And remember, in calculus, I always show you the long way, and then I show you a shortcut eventually. Okay, so you have to know the long way, though, because it's all over the AP test in the multiple choice section, especially. All right, so here we go. So let's ignore the limit part, and let's just talk about just this part right now. Okay, it does not look like any of my formulas. Let me go back to my 4 formulas. It doesn't look like any of these right now. Okay, so I need to figure out how to get it into a form that I recognize. Okay, I want to see only I squared, or only I, or only I cubed. So I want to be able to break things apart. Okay, so I'm going to simplify by going ahead and FOILing out this 1 plus 2i over n times itself. So that's the first step I'm going to do. So when I do that, I get 1 plus 2i over n plus another 2i over n plus 4i squared over n squared. Be very careful with your powers. That's where a lot of people mess up. A lot of people will do 4i over n squared. Okay, so that simplifies to 1 plus 4i over n plus 4i squared over n squared when I combine those two in the middle. Now we're multiplying by 2 over n. So when I do this, I get 2 over n plus 8i over n squared plus 8i squared over n cubed. Okay, so that's what we're going to work with. So we're going to say sigma I equals 1 to n. Sigma's very similar to limit. You always have to write it. It's very annoying. So we're writing it every time. And we're going to have 2 over n plus 8i over n squared plus 8i squared over n cubed. Okay, and we know that with a sigma, we can break things apart. So if I have pluses in between there, then I can break them into separate sigmas. So that's exactly what I'm going to do. So I'm going to break it into I equals 1 to n of 2 over n plus I equals 1 to n of 8I over n squared plus I equals 1 to n of 8I squared over n cubed. Okay, and you can think about what each of these are. Sometimes it helps if you write the expanded form for a couple of them. So like basically for this one, you don't have to write it, but basically what's happening is you have 8 times 1 over n squared, and then you have 8 times 2 over n squared, and 8 times 3 over n squared. So if you think about what you can pull out in front of the sigma, it's everything that's in common, right? It's a common factor that we're pulling to the front. So what we have in common is the 8 over n squared. Okay, so I can pull that to the front of the sigma. The same idea with the 2 over n. There's actually nothing, like there's no I there, right? So what I'm going to do for this first one is I'm going to have 2 over n. I'm going to pull it to the front, but I still have a 1 as like a placeholder, right? So it was like 2 over n plus 2 over n plus 2 over n times. This next one is going to be the 8 over n squared, like I said, from I equals 1 to n of just I. The next one's going to be I equals 1 to, oops, sorry, I forgot to pull out the thing. So the next thing I can pull out, again, is the 8 over n cubed. Basically, you can pull out anything that doesn't have to do with that I, as long as it's being like multiplied, right? So we have I squared. And these pieces right here are exactly what we have in that little formula box that I gave you. Okay, so you can go back to those boxes. So if I go back there, they're right here. Okay, we have everything that we need on that page. So kind of, bookmark that page, get a little Post-it, because you're going to use it a lot on your homework. Okay, so if I have the summation of 1 from I equals 1 to n, that's just n. Okay, so I end up getting 2 over n times, that all just becomes n, right, because it's 1 times n. Plus, I'm going to have 8 over n squared, the summation from I equals 1 to n of I, right, that's the Gauss formula. That's the n times n plus 1 all over 2, because it's 1 plus 2 plus 3 plus 4 plus 5 all the way to n. And then the last one, the summation for the I squared part, right, so that was this. The I squared part, that's the one that's a little bit harder. That's the one that's the n times n plus 1 times 2n plus 1 all over 6. Okay, so I'm going to have n plus 1, 2n plus 1 all over 6. Okay. So at this point here, we're just relying on your algebra skills. And it does get a little bit messy, but you can do this, I promise. Okay, so if you want to try to clean it up, you can always kind of pause, try it on your own. The first part, the n's are going to cancel. See how those n's go away? So I just have a 2 to begin with. Okay, the next part, the 8 and the 2 reduce out to be 4. But I'm going to have to multiply out the n times n plus 1. So I'm going to get n squared plus n all over n squared. And then the 8 and the 6 reduce down, right? They're divisible by 2, so I get 3 and 4. And then n cubed and an n will reduce down to an n squared. But I'm going to have to multiply, like FOIL this part out, okay? And you'll see why in a second. So I'm going to have the 4 over 3n squared. And I'm going to FOIL it out, and I get 2n squared plus 3n plus 1. Okay, and I continue to simplify. Okay, so I'm going to have 2 plus 4n squared plus 4n divided by n squared. So I'm going to divide the n squared into both pieces, actually, like that. And then this is going to be 8n squared plus 12n plus 4 divided by 3n squared. So I'm going to do divided by 3n squared in each piece. Okay, and the reason that I do that I look at each piece individually is because the very last step, remember I told you to ignore this till the very end, is that part right there. So if I take the limit as n goes to infinity, so I'm going to kind of write this down. So what I have right now is I still have 2 I have my 4, I have 4 over n as I reduce down, plus 8 over 3, plus 4 over n, plus 4 over 3n squared. So all I did is I just divided, like here, 4n squared over n squared became 4, right? I just reduced everything down. And now I take the limit. So this is kind of bad notation because we know we should write limit every single time. But I'm going to put it in right there. So as I do my limit as n goes to infinity, so maybe I'll say, like a little implies that this is equal to, right? This will go to 0, the 4 over n. 4 over n will also, 4 over n will also go to 0. And 4 over 3n squared goes to 0, right? Remember, if I'm dividing by a huge, huge number, it goes to 0. So I get 2 plus 4 plus 8 over 3. I'm going to have 6 plus 8 over 3. So my answer is going to be 26 over 3. Or 8.6 for people. Okay? So that's the process that we're going to do. I know that that is totally overwhelming. It's a little bit hard, right? So that's why we have the office hours on Wednesday. So you guys can come to the office hours on Wednesday and ask questions. But let's do a few more examples. I know this is a very long section. The other sections aren't quite this long. Okay. So it says, let's revisit our last example. So suppose we have the curve y equals x squared. And we want to find the area between the curve and the x-axis from 0 to 2. Okay. This is more how your examples will be. We can partition the original interval into n subintervals. So what we did before is we used 4 subintervals. So we took that distance 0 to 2, a length of 2, and we divided it into 4 pieces. So each subinterval was 1/2. Okay, so let's think about it. If I have an interval 0 to 2 and I divide it into n pieces, I'm going to have lots of different tick marks. This first one is going to be at a distance of 2 over n away from 0, right? Okay. Because I'm dividing it into n pieces. So think about 10. I'd have 2 10s, right? I'd divide into the interval 0 to 2 would be divided into 10 pieces, and each one would be 1/5. Okay? So in order to do this, we use the equation b minus a all over n. Okay, that's equal to our width of each rectangle. All right. So it says since f is increasing, the minimum value on each individual interval is the left endpoint, and the maximum value is the right endpoint. So it's kind of weird, but we've talked about left endpoints, right endpoints. So a left endpoint will be here and going over, and here and going over, and here and going over, until we get these like little partitions, right? So the way I'm drawing it was like 4, but what if we have n? Okay, so we could have lots of different rectangles in here, an infinite number actually, and each of those would be used left endpoints, right, or right endpoints. Okay, the one that's going to be easier for us is actually going to be right endpoints, and I'll explain why. So if we use right endpoints, sometimes I draw the little number line, 0 to 2, and each width is going to be 2 over n, right? I talked about that. Then the first right endpoint is going to be at 2 over n. The second right endpoint will be 2 of those 2 over n's. It's going to be at 4 over n. The next one's going to be at 6 over n, 8 over n, and so on. Does that make sense? Because I'm going to have, this one was 2 widths. This one was 3 widths, right? This one was 4 widths. Okay, so the way that I talk about, if I want to talk about the ith right endpoint, it's always weird when they talk about i's and n's and so on. The ith one, so like if I wanted to talk about the 16th one, it would be the 16 times 2 over n, right? You have 16 of those 2 over n's to get to that right endpoint. So if I want to talk about the ith endpoint, it's going to be 2 over n times I, or 2i over n. Okay? So our width we always call delta x. So in this formula, our delta x is our width. This is saying our height. Okay, so when I use a capital M, it means the right endpoints. When I use a lowercase m, it's going to be the left endpoints for something that's increasing, right? The big number versus small number, the higher one versus the lower one. Okay, don't worry too much about the notation. Okay, you really just need to know how to talk about the upper sum, lower sum. Okay, so here we go. So the right endpoints. So I'll call it the right endpoints within rectangles. I'm going to have the sum from I equals 1 to n. I'm going to have the width times the height. Well, the height of all those is using right endpoints, 2i over n. Okay, so notice how this one, the width, did not have an I. It was just the width was 2 over n. We know that. And then the right endpoint, each one, depending on where we are along that number line, involves an I, right? If I want to talk about the 16th endpoint, it would be 32 over n. Okay, that's what we're saying. So we go back and we think about what function we have. So we have y equals x squared. That's our function. So when I'm doing this, what I'm saying is I have my width times my function, which is plugging in 2i over n into y equals x squared. So I do that number squared. Okay, if it had been x cubed, that would be that number cubed. And then it's just like that last example where we have to simplify. Oh my gosh, my pen is just wigging out today. All right, so I'm going to have I equals 1 to n, 2 over n times 4i squared over n squared, which is going to be I equals 1 to n, 8i squared over n cubed, like that. And then I think about what I can pull out. So I can pull out the 8 over n cubed, and I'd still have I equals 1 to n of I squared. Okay, and if you remember the I squared thing, that's the one that's n times n plus 1 times 2n plus 1 all over 6. Okay, and now it's just an algebra problem. You're just simplifying. So if you need to pause and try it, I recommend doing that. It's always best to try. Okay, so the 8 and the 6 reduce out and become 4/3. N and n cubed, n squared. I FOIL the top. So I have a 4, and then I have 2n squared plus 3n plus 1 all over 3n squared, which is going to be 8n squared plus 12n plus 4 all over 3n squared. So I get 8/3 plus 4 over n plus 4 over 3n squared. Okay, so if I finally take the limit as n goes to infinity, right, because that's really what we're going to talk about in the end. We don't want to just talk about a random n number. We want n to be infinity. Then what happens is this part and this part go away because you're dividing by a really big number. So we end up getting 8/3. Now, if we did the left endpoints, you'll see the left endpoints are actually harder. I know that I'm sure that you think the right endpoints are hard, right? I know it's hard. I've done this before. I remember being totally confused when I did this in calculus. That's why we have these office hours. Come to office hours if you get stuck. Okay? But the left endpoints, the reason they're harder is because you still have 0 to 2, and you still have a width of 2 over n. So we still get this one's 4 over n and 6 over n. But if I'm using left endpoints, I'm using this one and going over, right? So the first endpoint ends up being 0. The second endpoint, oh geez. ends up being the 2 over n. The third is the 4 over n, right? It's kind of confusing. It's like, wait a second. It's not quite what I want. The fourth ends up being the 6 over n. So if you talk about the ith endpoint, it's actually one less than what you would think it would be. Okay, because the fourth involved 3 of those 2 over n's. The third involved 2 of the 2 over n's. So the ith is going to involve I minus 1 of the 2 over n's. See how it gets kind of messy? So when you plug that into your function, so it says the lower sum. The lower sum ends up being our width, which is the 2 over n, times our function, which is going to be that I minus 1 over n times 2 over n. Okay, which is kind of messy. Because now you'd have 2 over n, you'd have this 2i minus 2 over n squared into your function, which is x squared, so y, that's our x value, so we square it for y equals x squared. And then you still have to FOIL it out, right? You still have to FOIL, you still have to simplify, and it takes a little bit longer. Okay, so if you were going to do this one, I'll try to do it kind of speedily. You'd have 4i squared minus 8i plus 4 all over n to the 4th. Sure, I'm making mistakes somewhere. These are always tricky. So I get n to the 5th. And then I'm going to have 8i squared minus 16i plus 8. And we still have to break it apart. So 8i squared over n to the 5th minus 16i over n to the 5th, oops, sigma, plus 8 over n to the 5th. And then you pull out those like common factors that we talked about. So you're going to have the 8 over n to the 5th summation of I squared. And then you're going to have minus 16 over n to the 5th summation of I. You're going to have plus 8 over n to the 5th summation of 1. And it just gets kind of messy. So you're going to do those 3 summation formulas here, here, and here, and you should get exactly the same thing. So provided I didn't make a little mistake in there. Sometimes I make mistakes on the left endpoints, it's complicated. So the one that it ends up being easier is the right endpoints. So always use right endpoints if possible. Because you don't have to like adjust by doing I minus 1. You already have like the 2i over n or whatever. Okay. All right, so one last thing. So it says if you're worried right now, I just want to remind you about derivatives. So didn't I teach you the hard way before I taught you the super simple way? Okay, so if you're freaking out, it's okay. I know that it's a difficult section. This is what I tried to warn you guys about. This is the hardest section. So the area under a curve using an infinite number of rectangles. So it says for a function f defined on a to b, if f is continuous, the area under the curve ends up being adding all of those rectangles together. That's what that's saying. You take an infinite number of rectangles, you add all of the width and heights together, which looks like this. Okay. Again, not super important that you understand like every single thing in that formula, but just know it's the width times height, and so on. So it says find a formula for the sum of n terms on the interval 0 to 2, and then find the limit as n goes to infinity. Okay, so let's kind of sketch it out to see what's happening. So if I have 2x minus 2, you can graph it if you want to. If you think about where it's crossing the x-axis, right, you can pull out an x. You'd have 2 minus x. So it's going to cross the x-axis at both 0 and 2. And it's going to be a downwards parabola. So it's going to look something like, whoops, missed it. Something like that. Okay, we want to find the area under the curve from 0 to 2. So we're trying to find this area right here, which kind of looks like a semicircle. Not quite, okay? So if I'm finding a formula, again, I'm just going to think about the width times the height, And this is the part that you're going to have to do for your homework. You're going to have to think about what the width and the height is in order to use the sigma notation thing. So we have from 0 to 2. Okay, so if you had 0 to 4 or 0 to 10 or whatever, then our width would be different. Okay, so if I take that distance and I divide into n subintervals, our width, again, is going to be 2 over n. Like I'm saying, it's not always 2 over n. It could be like 10 over n, right? So if I want to talk about, each one, right, I have 2 widths to get 4 over n, 3 widths to get 6 over n. If I want the I point, its right endpoint is going to be 2 over n times I, 2I over n. Okay, that's where we're getting that. So the height of that right endpoint would be 2 times 2I over n minus 2I over n squared, because we're using the function, we're plugging it in. So if we simplify a little bit before we put it into the sigma, we're going to have 4I over n minus 4I squared over n squared. Okay, so we just simplified a little bit. So my area is going to involve the limit part, which we'll leave till the end. So if you want to leave off the limit, it's fine. I won't yell at you for doing that like I did in chapter 1. All right, so it's going to be the width of each rectangle, which is the 2 over n, times the height of each rectangle, which is the 4I over n minus 4I squared over n. Okay, so this is where I want you to pause and try it. Try to multiply it out, try to break apart the sigmas, try to find your final answer. Okay. What I'm doing here. So I'm going to multiply it in. So I'm going to have 8I over n squared minus 8I squared over n squared. Oh, did I forget? Ah, you would have gotten a bonus point, n cubed there. Forgot my squared here. Okay. So as I do this, I'm going to have the 8 over n squared, and then the I. I have a minus 8 over n cubed. Geez. And then I squared. Okay, and then both of those are from our sigma formulas. Our summation formulas. All right, so if I have the I, I have n plus 1 over 2. And then if I have the I squared, that's the one that's n times n plus 1 times 2n plus 1 all over 6. And we just simplified. So here's algebra. So I continue to simplify. So I get 4n plus 4 all over n. So I'm going to bring that over n into both of them, actually. I'm going to shortcut it. So over n over n. Now we have 8n squared. Oops, this is all going to be minus, right? So there's a minus in between. We're going to minus 8n squared minus 12n minus 4, and then those are all over 3n. So as I simplify, I get 4 plus 4 over n, which will go away, minus, uh-oh, should I leave off an n? I forgot my n cubed again, didn't I? Dang, I keep doing that. N cubed. So this is n squared then. Basically, I knew I had made a mistake because all of those should reduce out. Like I shouldn't have anything with like an n on top because that would go to infinity. I should have all of the n's on the bottom in the end. So I have 8 over 3. Ugh, terrible handwriting. 8 over 3 minus 4 over n minus 4 over 3n squared, which this will go to 0, and this will go to 0. So we're going to have 4 minus 8 thirds. which is going to be 12/3 minus 8/3. So our answer should be 4/3. Okay, let me check real quick, make sure that I have the right answer. Because I made a couple errors. You guys had a chance for a bonus point, and I just found them. I'm sure that you guys were hating me as you were doing that. All right, so 2x minus x squared. Okay. Yeah, so that is the answer. So the actual answer is 1 1/3, which is 4/3. So we are good. So that's how we do those. So see how they can be very, very time consuming. Like I said, I'm hoping that you guys did this in multiple sections, like you kind of just took your time, paused, thought about it. The next section is actually a little bit more practice. So I'll do a couple more examples to help you with your homework. And then after that, it's very easy. Okay, so these are the worst sections of J-term. So if you get stuck, definitely come to office hours because I know that it can be super tricky.